Welcome to Physics 142 Online again. I'd like to do a fairly complicated example problem that asks us to find the force between two charged objects that are not point charges. It's actually a pretty difficult problem to do unless the objects have special simple shapes. So we're going to do a problem that asks us to find the force between two objects with those fairly simple shapes. So read the problem. You can see that we're trying to find the force exerted by a uniform thin ring of charge with radius r, it's illustrated in my crude little sketch, and a total charge plus q, the force that exerts on a thin rod of charge of length L and total charge capital Q. And the thin rod is sitting on the axis that I'm going to call the z-axis, which is the axis that passes through the center of the circular ring. And the two objects are separated by a distance a. So we would like to use Coulomb's law and our knowledge of calculus to find an expression for that force. And as always, what we're going to do is divide one of these objects, and in this case we're going to divide up the rod into small pieces. And so when we do that, we'll say that there's a charge element dq on a little slice of that rod, and since it lies along the z direction, then we will call the size of the element dz. Okay? So that the amount of charge that's on that charge element will be, if it's a uniform charge, it'll be the total charge q divided by the length of the rod, so the charge per unit length multiplied by the length element dz. And we've done this before in other problems. We're also going to make use of an expression that was derived for this thin uniform ring in the textbook. So if you look at the example on page 72 of the text, which is equation 8.8, that equation tells us what the electric field is produced by the thin ring of charge at a point on its axis, a distance z away. And so that equation says that E produced by the ring at a general point on the z-axis is the Coulomb constant K times its charge Q times z divided by z squared plus the radius squared, all to the 3/2 power. And the electric field, if this is a positively charged ring, is in the z direction, the k hat direction. So I've copied that formula directly out of the textbook. Now, why are we using this formula? The reason is, if I know the electric field produced by the ring at any point on its axis, then I can calculate the force it produces on a charge on the axis. And we have an entire rod, so I can't use the formula directly, but what I can do is use it to calculate the tiny amount of force on this element of charge. Because this element of charge is so small, we can treat it like a point charge. So the force of an E field on a charge Q, this comes directly from the definition of the electric field. The force is equal to the charge times the electric field. See, so if I know the electric field of the ring, then if there's a point charge Q sitting on the axis, I can multiply Q times the field and get the force. Well, here what I'm going to do is find the element of force, which we're going to call dF on the charge element dQ. And I can just copy this down from the force equation. So dF, the differential amount of force F, is equal to, in this case, dQ, the charge element of the rod, multiplied by the electric field of the ring. And I'll write the subscript ring here, but I'm going to drop this because we understand that that's what this electric field equation does. So I can write down then by making the substitution for E, the E of the ring, I can write down what the differential amount of force is. And I'm going to drop the vector signs because the electric field is along the z-axis, and if the rod is positive, then the force is also along the z-axis. So all of these contributions to the total force will be along the z-axis. So this is simply then K, Q, Z, dq, that's what's in the numerator when I multiply the field times dq, divided by z squared plus r squared to the 3/2. And now I can take the expression for dq, the charge element, and plug it into the equation as well. So when I do that, I get k little q big Q z dz. I collected all the terms that end up in the numerator when I make the substitution for dq, and the term that ends up in the denominator, in addition to what's already there, is the factor of L. So I get L times z squared plus r squared to the 3/2 power. So let's stop for a minute. What this means is a piece of the rod that has a length element dz experiences a force dF given by this equation here. So in order then to do the integration, I just have to set up the appropriate integral. And actually I don't want to use the force vector because I know that we're calculating the magnitude of the force, and the direction will be in the k hat direction. So F then is the integral of dF along the entire length of the rod, and so that will be the integral of this whole quantity here, k q q z dz over L, oops, I'll put the z squared first, z squared plus r squared to the 3/2, and the limits on z begin and end at the ends of the rod. So the bottom end of the rod, what I need to put in here just so we understand exactly what z means. Remember, z is the distance away from the center of the ring where we want to know the electric field. That came from the electric field equation here. So just to make it really clear, the charge element is at a distance z away from the center of the ring. So the coordinate z is measured from the center of the ring. That means the bottom end of the rod, which is the lower limit on the integral, is z equals a, and the top end of the rod is at a plus L, z equals a plus L. So I've got the proper limits. The next step is to pull everything that's a constant outside of the integral and realize exactly what it is that we really have to integrate. So in the numerator, the k times the product of the two charges comes out, the denominator, the L, comes out, and what we're left with is the integral from a to a plus L of z dz over z squared plus r squared quantity to the 3/2. And that's all there is to it. The physics is basically done at this point. The mathematics still takes a few steps, and I'll show you how to do that, but it's most important to understand the setup. And what we did, once again, knowing the electric field produced by the ring at a certain point, we then carved the rod up into tiny little elements, calculated the tiny amount of force, dF, on each one of those elements, and once we got that into the right form, we could then perform the integration along the z direction. It adds up the sum of all those forces starting at the bottom end of the rod all the way to the top end of the rod. So what we're calculating now is the total force of the ring on the rod. And this integral, it can easily be done using a u substitution. And so if we let u equal z squared plus r squared, what's inside the term in the denominator, what's inside the parentheses, then du will be 2z dz, okay, And then what we can do is make the substitution, because the z dz term is what's in the numerator already, and that will simply be, right, 1/2 of du will just be z dz. All right, so if we make this substitution, then we get the force is k little q big Q over L, and we'll have to fix the limits in a minute. That won't be too much trouble. That means then the numerator is the 1/2 du. The denominator becomes just u to the 3/2. And see, what's left to integrate now becomes really easy. We see that we can do that directly. The only thing we have to be careful about is the limits. Let's see, the limits before were the value of z, and so we have to write down what the value of u is. So if z is equal to a, then u would be a squared plus r squared. So that's what's the lower limit, a squared plus r squared. The upper limit then, if z is equal to a plus l, then u, well, it's going to be kind of have trouble with room here, so let me erase something to give myself a little more room up here. Good. So now I can put in the upper limit, which is going to be a squared plus l squared plus r squared, right? Because if z, whoops, nope, I made a mistake there. Let me fix that. Bad mistake. That would have really derailed me. U is equal to z squared plus r squared. We want to let z be a plus l. And so what we have then is a plus l quantity squared plus r squared. That becomes the upper limit. All right? So the 1/2 can come outside. We get k q over 2l. And then the integral is just the integral of u to the minus 3/2 du. Now the limits, I won't rewrite those just to save a little bit of space here. So that becomes k q over 2l, and this, I believe, is going to give me minus 2 times the quantity u to the minus 1/2. If I've done that right, and I'll just check that mentally, if I differentiate what's inside the parentheses, I'll get a negative 1/2, which will cancel the minus 2, and then I'll get u to the minus 3/2, which is exactly what I want. That's good. So the limits on this, now I'll write those in again. The limits on u now are, lower limit is a squared plus r squared. The upper limit is a plus l quantity squared plus r squared. And now I'm going to need a little bit more space. So let me scroll down just a bit, give myself a little more space in doing this. So what this gives, if I make the substitution, oh, look at the 2's cancel out. So if I pull minus k big Q little q over L again, and now I've got the first term is going to be u to the minus 1/2. That's the upper limit. So it's 1 over the square root of this whole quantity here, which is a plus l squared plus r squared, right, minus 1 over what we get for the lower limit, which is square root of a squared plus r squared. And the only thing I'll do with this, I get the minus sign out front, and I'll just rewrite this as k q over L, and then reverse the order of what's inside the brackets. Not necessary, but it will make it clear that my answer is indeed positive. Now, what more can we do from here? The question at the very outset asked us, once we get the answer, and this is the answer right here, this is the exact result, it asked us to check to see if, when we take the limit, that A, the distance, remember, between the ring and the rod, if A gets really large, so we pull the ring really far away from the rod, or pull the rod far away from the ring, if A gets large compared to R, the radius, and compared to L, the length of the rod, what do we see as the approximate answer? And we ought to expect from previous work that if you take two charged objects and pull them really far away compared to their sizes, that we should get back a result which looks like the force between 2 point charges. And that's really not obvious from what we see here. It really is not clear that somehow this is going to reduce to the result for the force between 2 point charges. So what do we do? Well, what we can do first is evaluate those square roots in the limiting case, first of all, where, okay, if A is much greater than R. All right, let's take a look at what we get. If A is much, much greater than R, that's what the double inequality sign means, then the square root of A squared plus R squared is essentially the same as just the square root of A squared, or just A, right? And likewise, the other square root term, the square root of A plus L squared plus R squared, if A is so big that we can neglect the R that's in that term, that becomes the same as the square root of A plus L quantity squared. The square root of that is just A plus L. See, these are approximations, of course, but that's what we want. The exact answer we already have. Now we want the approximate answer in this limiting case. Now, let's take a look at what we get there. Okay, so using those two approximations, we now get that the approximate F is K big Q little q over L, and we now get something that looks a little bit more reasonable, 1 over A minus 1 over A plus L. What do we do with this? Well, we can now look at this and try to get both of those two fractions over a common denominator. And I think you can see how that's going to play out here, because I'll multiply the top and bottom of the first term by A plus L, and I'll multiply the top and bottom of the second term by A, so that I'll get everything over a common denominator. And I think I have just enough space here to show at least most of the answer. This is going to give me A plus L minus A over A times A plus L. And look at what happens. This, the A plus L minus A, well, in the numerator, the A terms cancel. Then, what's left in the numerator is L. Well, L cancels with what's in the denominator of the other term, the KQQ over L. So what we're left with is K big Q little q over A times A plus L. And now, let's just take the final step. If we look at that answer and realize that we also want the limit where A is much, much greater than L, then the denominator becomes not A times A plus L, but just A times A. So we're left with this approximate force, having made the approximation both that A is much greater than R, and now A being much greater than L as well. We get K Q Q over A squared. And look at that for a minute. Let's go back to the picture. Right? Capital Q is the charge on the rod. Little q is the charge on the ring. If they're really far away from each other, then the force between them should just be the Coulomb constant times the product of the charges divided by the distance squared. And that's exactly what we get. So, what this does is it gives us some confidence that our answer is the correct answer, because we checked to see if it reduced to the approximate answer of the force between 2 point charges. And that, since it does, that gives us some real confidence that we've done the problem right, because it makes physical sense. Don't forget the correct answer, the exact answer we already have, and that's right down here, but finding out that it matches the expected answer in a particular limiting case is a really good thing to do. If you've understood this problem, I think it will help you a great deal in setting up at least one of the homework problems that involves the charge between the force between two extended objects. I'll see you in class.